Hello guys, welcome to VCBA. In this video, we are going to discuss about Cascode configuration of BJT. This is also one of the biasing of BJT. Before starting into this lecture, I want to discuss about what is biasing and why do we need biasing. Biasing means applying voltage sources to the given network. And why do we need biasing? We need biasing in order to stable the BJT. Based on the biasing, BJT stability will vary. There are many biasing techniques such as fixed bias, emitter bias, and voltage divider bias. In this video, we are going to discuss about cascode configuration of BJT. What is meant by cascode configuration? In cascode configuration of BJT, it will ties the collector of one transistor to the emitter of other. In essence, it is a voltage divider network with a common base configuration at the collector. The result is a network with a high gain and a reduced Miller capacitance. We generally bias BJT in order to get high gains. Picture on the left side is cascode amplifier and picture on the right side is equivalent DC of cascode amplifier. We will start DC analysis by making an assumption that the current flowing through these biasing resistors R1, R2 and R3 is much greater than the base currents. That is, IR1 and IR2 and IR3 is much greater than IB1 or IB2. The result is that voltage at the base of transistor Q1 is simply determined by application of voltage divider rule. Since the resistors R1, R2 and R3 are in series, by applying voltage divider rule, we can get the voltage of the base at the respective transistors. Similarly, the voltage at the base of transistor Q2 is found in the same manner. Now, we will try to find emitter voltages of both the transistors. We know what is the value of B2 and also the value of B1. We know that VB1 means VB minus VE, and based on that equation, we will obtain VE1 as VB1 minus VBE1 and VE2 as VB2 minus VBE2. The emitter and collector currents are determined by this equation. As beta value is very large compared to 1, we can make an assumption that beta plus 1 is nearly equal to beta. So, by that assumption, all the four quantities IC2, IE2, IC1 and IE1 are nearly equal. To determine IE1, IE1 is the current flowing in this direction. So, we can determine IE1 by VB1 minus VBE1 divided by the respective emitter resistance. Similarly, we have to find the collector voltage VC1. If we observe, the collector voltage of the first transistor and the emitter voltage of the second transistor are equal. As we know what is the value of VE2. VE2 is determined by this equation. VE2 equal to VB2 minus VBE2. So, as per the diagram, VC1 is equal to VE2. So, the collector voltage of the first transistor is equal to the emitter voltage of second transistor. And collector voltage VC2 is obtained by applying KVL at this loop. VCC minus IC2RC equal to VC2. Now, our final step is to determine current through the biasing resistors. As we made an assumption that the current flowing through the base terminal is very small, then R1, R2, R3 will be in series. So, we can determine current by simply calculating the effective resistance. So, current through the biasing resistor is equal to VCC by R1 plus R2 plus R3. As previously we determined what is the value of IC1 and IC2, we can also determine base current by this equation. IB1 equal to IC1 by beta and IB2 equal to IC2 by beta. That's it for this lecture. Thanks for watching.